Thank you. Good morning. Back in 2019, Apple at their Worldwide Developer Conference announced they were making a dramatic change to the way they were dealing with the kernel space on their Mac operating systems. Today, I'm going to be dealing with one of the results of this, namely the Endpoint Security Framework, or the ESF. I am a senior researcher at WithSecure within their Countercept team. Prior to being part of the research team, I was a threat hunter for 4 years. I have produced multiple white papers and proof of concept detection codes and presented at a number of international conventions. So what are we going to be going over today? We'll be going over what exactly the ESF is, why the ESF is important to the detection industry, how can we in the industry utilize the ESF, some of the issues during implementation and some of the solutions that I found to these issues, my devised POC solution, which I codenamed esfang, and briefly going over a use case against the Meterpreter agent. So first off, what exactly is the ESF? So the ESF is developed as a kernel-based telemetry acquisition system by Apple, and it's been developed as a way for a one-stop shop for telemetry needs from the security industry. As we said, it works in the kernel space, and because of that, it actually works fairly similar to the way the ETW works inside the Windows operating system. In many ways, it succeeds the OpenBSM, or the Open Basic Security Module by Sun Systems, that was used primarily for auditing purposes prior to ESF. And one of the great results of ESF is that it allows for real-time event acquisition for direct intervention on real-time interception. But what does this exactly look like? So the image on the right here gives a very basic overview of how this works, from the user space at the bottom with a endpoint security application feeding into the kernel space and getting messages from the kernel space for the telemetry. And on the left is a demonstration of that information, which from every single event type includes multiple low-level data points, including the parent process ID, path, environmental variables, CD hashes, and so forth. But why is the ESF important? So during the presentation at the Worldwide Developer Conference in 2019, they announced they were going to deprecate KEXT, or kernel extensions. Primarily, this means that they were removing third-party kernel extensions from the kernel space, meaning that third-party security vendors could not use their own kernel extensions for telemetry acquisition. Because of this, they introduced something called system extensions, which is their way of allowing kernel extension, proprietary Apple kernel extension access from the user space using something called system extensions. Equally, before ESF came along, OpenBSM, as I said, was a primary auditing tool, but it was quite clunky to use and fairly difficult to integrate. There's lots of documentation on the problems with OpenBSM, so I won't go into them. But needless to say, ESF is a much easier solution to getting these telemetry points. So let's have a look at the old way of how monitoring worked. So at the bottom, we have the user space, top kernel space, and on the left, the logs. So what would happen is that third-party vendors would have their monitoring program hooked into a third-party kernel extension running in the kernel space and acquire telemetry via that point. Then, using OpenBSM hooks, they would hook into log files and acquire them through an auditing process, run them back through the monitoring program for detection processing. The new way is slightly different. So as we said, the system extensions work in the user space, and they work on frameworks that were introduced by Apple to directly access kernel space using their proprietary kernel extensions. These work out as the Network Extension Framework, Endpoint Security Framework, or ESF, and the Driver Kit Framework. And using an amalgamation of the three, you have very high visibility over the low-level telemetry of the operating system. However, we're focusing on the ESF, and from that, it actually hooks into the Endpoint Security Kernel Extension, again developed by Apple, so it allows them to have this proprietary pipeline from the user space system extension to their maintained kernel extension. But why make the change? So one of the primary reasons that Apple made the change to remove kernel extensions was for increased stability and security. So by removing third-party kernel extensions, you avoid things like the black screens of death, but equally you avoid third-party malicious kernel extensions from being introduced into the operating system. This means that they have much greater control over what is happening in the kernel space, and it just eliminates a lot of the overheads and a lot of the problems that are being encountered with less stable kernel extensions that we're finding in the wild, and it means that everything becomes very uniform. One of the things to note about kernel extensions is that even though they've been deprecated, they can still be used. You have to dramatically reduce the security profile of a Mac operating system in order to do so. Primarily, you used to be able to introduce kernel extensions on the fly, on demand. However, now you have to degrade the security profile that's running. Then you have to turn on kernel extension and then reboot the system, which means you can't just inject them as you would. But how can we use the ESF? So this slide's a little bit messy, so I'll just walk you through it. So in the bottom right, you'd have the main code running in the user space of your program. You would then create an endpoint security client object. This would then subscribe to the endpoint security kernel extension with the event types that you want. So you specify the event points you want, like file creation or process creation or anything to that sort of thing. The endpoint security kernel extension then populates an event message queue in the kernel space, and then pipes that out to your endpoint security client, which you have already subscribed, which you use to subscribe to the kernel extension. Then on each message, a callback is generated, which you can have a callback monitor, and then each message that's received can be processed back into your main code for detection purposes. But what are some of the issues with the ESF use, and what are the solutions? So during my experimentation with ESF back in early 2020, there were a number of solutions that came out from multiple researchers and vendors, but there were some very primary issues that came out with its utilization. Namely, a bottlenecking issue, system verbosity, and a real parent process ID issue. I shall go through each individually. First of all, a bottlenecking issue. So this was actually something that I was banging my head against for a couple of weeks, even a month, 2 months. And effectively what was happening is where you were doing exactly the same experiment, you would get different data points being populated and you'd have different numbers. And it didn't really make any sense as to why. So you'd conduct the same malicious experiment using the ESF telemetry acquisition, but you'd always get mismatched data points, and you'd have data points that were being missing for no particular reason. And equally, from a detection perspective, this means that it's inconsistent, and therefore the data points are unreliable. And it was a very long-standing reason before I figured out exactly why this was. Primarily, the issue was caused by the kernel-level queue. So you may remember from the previous slide, I said that the kernel extension inside for the ESF would populate a queue within the kernel space. But what was happening is this queue was being overloaded because the amount of data that you were subscribing to was simply too much. So if you try to subscribe to too many event types, the queue gets overloaded and silently drops data packets, which then don't come back to the user space. But there's no indication that this happens. So although the data packets are dropped from the kernel side, because the kernel side is obviously secure and it's isolated, you don't get a notification that this has happened, which is problematic. Two primary solutions to this are a development solution and a ESF proprietary solution. I'll go over the event muting first. So event muting is a function that was built into ESF. And what it does is it allows for specification for events to be dropped inside the kernel extension space. Now, what this means is that through process path or process token, you can specify particular event types to be dropped on the kernel side and not published into the event message queue inside the kernel extension. Because of this, it means that you can avoid overloading. However, it's quite a blunt tool back when I was experimenting with it, because you either had to specify an entire process path, again, assuming it hasn't been hijacked by anything, or you had to do it by a process token, which only worked for that instance of the process. It was either too much of a sledgehammer, or it was too unspecific. It wasn't targeted enough. So for a viable solution, event muting just wasn't specific enough for effective filtering. Multi-client system, however, did turn out to be very effective. So whereas you would have an endpoint security client within a process subscribe to event types, instead of having one client subscribe to multiple event types, you could have multiple clients subscribe to individual event types, which equally generated their own queue within the kernel space. And by using this method, you don't get overload, and you get all the data you require, and you can conglomerate them into one data set and then run it through your detection stack by cross-referencing, which was very effective. One point to note is that the original development was on SDK 10.15 for Catalina. This was when ESF was introduced. But between 10.15 and 10.15.4, the SDK was suddenly updated, one with a number of new event types. They create something called the sec_num or sequence number in the ES message. So whereas I was saying before, there's no notification from the kernel that silent drops have occurred. That is still the case, but by using the sequence number, you can see whether there's a gap in those sequence numbers to see whether a message has been dropped due to overloading. So it doesn't alert you per se, but it does allow you to filter that data and detect when it's happening, and from that do things like dynamic rebalancing in order to prevent overload. System verbosity. If you look on the image on the right, you'll see that the original UID is 0. This is the system user ID on the system, on the operating system. And because it works at the kernel level, it ingests all the processing and all the file information for the system as well, including system daemons and system level proprietary management systems. And this creates a problem. Because we've talked about the bottlenecking issue before, the simple amount of data that's being processed by the ESF, when you take into account the system events, is extremely high. And because of this, you end up with a sort of overhead issue where you have to either filter out these system-level events, or you have to allow them, but then do additional filtering for anomalous indications. So one of the things, again, is that you could do it either before or after collection. So before collection, as we said, would be by event muting. But as I've said before, this is quite a blunt tool. And to use this for this sort of activity, it means that you'll be dropping. The only way to do this would be to drop all processes running at the system level, which can introduce ignorance of system level compromise, which could be very dangerous. So instead you have to look at client-side filtering, but then you look at the bottleneck issue that I mentioned before. And even when you start to filter down the event types into individual clients, you still run the risk of data events being dropped simply because the system-level processing event generation is just so high. So it becomes a balancing act between the two. There's no real one-size-fits-all solution for this, so you have to sort of balance this dynamically as well as possible. Parent process ID issue. So this is an ongoing issue in the Mac operating system. Primarily, this relates back to identifying where the original process was spawned from. So this actually goes back to things like XPC proxy, launchd, and more recently something called running board. So you may see at the top there's a real PPID of -1. This was actually by using a PPID solution. But as you can see, because it was running on a newer operating system, the result has actually come out as -1, which is incorrect data, just to demonstrate that this is actually an ongoing issue that there isn't really a permanent solution for. At the bottom, you can see that there is launchd being XPC proxy being launched by launchd, but that doesn't necessarily indicate where an original process was called from. The reason for this is because of how cross-process communications work in macOS, it's not really that easy to identify what process was initiating another because it jumps through these other programs. So when you start to go back to the process chain, there can be gaps due to these underlying system processes. As I've said, there is no real future-proof solution. The real reason for this is that Apple keep changing the way that this cross-process communication works for process spawning. So anytime a solution is made for one operating system version, it can be made obsolete by the next update, which, as you can imagine, is fairly frustrating. The current solutions that I was looking at the time were TrueTree by Joan Bradley and LaunchXPC by Patrick Wall. LaunchXPC was actually a solution that was implemented in my esfang solution, but it doesn't take into account running board at the time, which means that, as was demonstrated by the -1 real PPID, it is not a fully fledged or conclusive solution to this. And as I said, this is an ongoing problem that there isn't a one-size-fits-all solution for yet, and it was beyond my scope to try and figure that one out. So looking at the solution that I developed, or my POC, which I codenamed esfang. So first off, I need to shout out to Patrick Wardle, Chris Ross, and Omar Ikram. They, back in the early 2020, really set the stage for how ESF could work, the sort of telemetry acquisitions and really basic fundamentals of how to ingest ESF data. And my POC was based primarily off of their work and then expanding on it and introducing capabilities and solutions that I mentioned before for some of the issues that I encountered. My solution was actually developed early in 2021, and it was based off of 52 event types back in SDK 10.15.4. The primary reason that I did this was that the old solutions had a fixed definition of what event types it would ingest. And as I said before, this meant that overloading could occur because it was a fixed number of event types, which you couldn't necessarily deviate from, which if it was causing eventing, you couldn't change from the rigid structure. However, the solution that I put in was a dynamic solution. So this allows you that each boot, you can specify which event types you want to subscribe to. So you can have multiple esfang instances subscribed to different event types, or you can have them subscribe to multiple event types or group types like file creation data or file metadata, UIPC data, cross-process communication port data, and things like that. Using this solution, you can avoid the overhead, the bottlenecking issue. When I started this, had never coded in Objective-C before, so doing multi-threaded processes to achieve this as a standard solution was actually a bit outside the scope, but it should be easy to do moving forward from any Objective-C programmers out there. One thing to note is that because this was not done with an Apple Developer ID, it is a POC code, so SIP has to be disabled, or system integrity protection. So ESF cannot be accessed with SIP enabled unless the program that you're using has been signed by an Apple Developer ID. So if you want to use this for testing purposes, you have to disable SIP on your system, so this isn't viable for production level systems. The other thing is that it was designed for JSON output for upstream integration. So all the output is put into JSON format so it can be easily piped up into a database for further detection, processing, and easy acquisition by Elastic or threat hunting teams to those data sets. So let's go over the Meterpreter use case. The use case was done on macOS 11.2.2. I used esfang to collect all the data, and this is for the agent only. So this isn't to do with the Metasploit framework's capability that can be piped through the Meterpreter agent. It is only for the native Meterpreter agent capability. This is only done on the post-exploit phase, so I'm not interested in how the agent got onto the system, only what the agent can do once it is on a system. And this was done only against a single host, so not against an enterprise interconnected sort of demonstration. So it's not necessarily representative of a real-life attack, but it's to demonstrate what ESF's telemetry is capable of. So the overall findings, again, the graph on the right is very small. It's a representation of all the commands that were executed and the data that was generated. As you can see from the top solution is actually webcam streaming, which is not OPSEC, obviously. And as you can see, it generates a massive amount of data. But as you move further down, you can see that some of the data, some of the commands generated seemingly none or very little event types. But I will go through some of these to demonstrate some of the data values that can be found. So during the install, you can see that open, read directory, mprotect were the highest event types that were generated through ESF for Meterpreter installation. Now, memory protect and memory mapping for new processes, you expect this to occur, and memory protect being that high is actually not that anomalous, even though it's quite a high number. But if you turn this against what a normal process would do on the Mac estate, it actually doesn't stand out as that anomalous, especially when you look into the internal data. The open event, however, is slightly more anomalous alongside the FCNTL or file control events. The reason for this is that during deployment, the amount of file that it accesses in order to enumerate number of system enumerate the system information, and equally to change certain file access controls can be indicative of a Meterpreter deployment. So actually looking at these two specific event types does allow you to profile Meterpreter installation on a Mac operating system. So breaking down that slide a little bit further, in total, 259 data points are generated during a Meterpreter installation. But 259 data points doesn't necessarily mean that they're great data points. Quantity is not always an indicator of quality. But if you have enough data points with enough cross-referencing, you can generate more accurate profiles and higher fidelity, as long as you know what you're looking for. And ESF, during my experimentation, showed that it had both quantity and it had quality event types. So by filtering the two together, you actually get a very accurate representation of when anomalous behavior has occurred. But let's look at some of the other event types that are generated and against what sort of commands. So on this slide, again, so this is to do with file open events. So on the far right, you can see webcam stream of 478, and it's not operation secure, so that stands out like a sore thumb. Process listing is slightly different. So for each process that's running, it opens an individual file for each process to see whether it is running. When you look at that event type individually, you can actually filter out that it's scanning each individual process's file, which is quite easy to profile. If you already know what processes are running on the system, you can just scan for is a process scanning for all the running processing files and detect against that. The screen share and system information follows the same sort of process. So in order to enumerate and gather information about how it's going to screen share, it has to open up a number of system files, and system information, it does the same way as it does for process listing. Instead of using general system information commands from the bash terminal, it instead accesses a number of system files on the operating system in order to enumerate that information. Notify write, this is a really interesting one. So edit file, when it targets an individual file to edit, it writes the information to the file, and you get one write event. Upload is slightly different. So when you upload using Meterpreter, instead, as it's transferring the data from your attacker machine to the compromised machine, each packet is appended to the file routinely as it's received, which generates this huge number of write events to an individual file. But the write size is quite small, and it actually corresponds to the size of network packets being received by the Meterpreter agent. So from this, you can actually target one processor targeting one other file and a write event and doing it in very small increments repeatedly, especially if you filter out things like internet browsers and things like that. You very quickly can isolate when this is occurring. IOKit open is another interesting one. So this is to do with driver or hardware access. And again, you'd expect to see webcam stream 220 because it's hijacking the webcam stream's data feed. But screen share, again, because it's hijacking the user interface display feed, it equally generates IOKit event types. And again, IOKit is not something you see commonly. It's quite a low generated event. So finding any IOKit events outside of system UID is quite anomalous and makes it very easy to identify when malicious behavior is occurring. This is a list of some of the valued event types done against other that I've isolated from other investigations against things like MacShell Swift, Sliver, Merlin, and other attack frameworks. One of the interesting ones, one of the primary interesting ones is on the right there for PTY grant. The reason for this is that PTY grant is for pseudo-terminal generation. So for a dynamic user session, instead of piping the command through a bash terminal like you normally would, instead, MacShell Swift generates a pseudo-terminal, which is a master-slave comparison, and actually executes the commands that way, which is slightly weird, and you don't see that very often. So, in summary, ESF is extremely powerful, and it's very clear that Apple is taking the time to really look over the problems that are occurring during its use, and equally to refine the event types that are available. During the progression from SDK 10.15 to SDK 10.15.4, the number of event types increased, but equally so did the capabilities of detection when the system wasn't necessarily doing what it was meant to. Because of this, it's actually quite reassuring knowing that Apple have made this not really optional due to the deprecation of kernel extensions from third parties. And the fact that they're actually maintaining this shows that they realize that they've taken that control away from the security industry, but are actually taking steps to provide all the information and the stability that is required. As we said, some of the teething issues to begin with have been addressed, but there are still more that exist, and during more and more experimentation, they will rear their heads as we go forward. As I said earlier, compared to prior solutions, especially developing your own kernel extensions or using OpenBSM, which is very clunky, ESF is very streamlined. It's very easy to integrate into your existing stack. And because of this, it makes integration and development on it very easy from a security development standpoint. Looking at the use cases and some of the other experimentations that I've done in the past, it does mean that the detection capabilities that are available are very high. And it means that moving forward, we were able to create better detection profiles based off the ESF telemetry that is available and equally expanding event types that they're allowing. The final point to note is that, as I've mentioned, the number of event points that are generated, especially because of the system level and equally because of the low-level telemetry that's available, is very, very high. And because you don't have control over the kernel extension itself, filtering is absolutely essential. And it becomes not optional. And it's one of those things that we're just going to have to deal with moving forward when developing using this system. That's my email. That is the GitHub with the esfang source code. If anyone has any questions, please feel free to email me afterwards. We do have some time for Q&A. So if anyone has any questions, please go for it.
So if anybody has questions, please come in front here to the first mic. Just come to the mic here. Yep. Yeah, thanks.
So thank you for the talk. I was wondering from a perspective from a blue team, what kind of events I can find when I'm looking at the telemetry, because I'm more familiar with the Windows events, and sometimes we can find like credentials, passwords, what's not good, so we have to remove them. Do you know if there is something in place that remove this PII data, or do I have to do it with myself?
Yeah, that's a great question. So you'd have to do this all manually. The events that are generated by the kernel extension themselves are raw. So when you get them from the ESF client side, they can't be tampered with from the kernel extension side. So it would all have to be filtered on the client side itself. And there's no way of doing this further up the chain.
Okay. So if I decide to ingest this in some like Splunk, so I have to take care of this?
Yes.
Okay. Okay, cool. Thank you very much then.
No problem.
You mentioned that there's the user space component that is registering for the filters or for events. Sorry.
Yeah.
2 questions basically. Is there also an unregistered element that I can, for example, call if I'm doing a red teaming assessment and I gain access to this user space component? Can I then call an unregistered event that I basically disable monitoring for that?
So because the event monitoring has to be done something like that, and it's done by an individual endpoint security client object inside the process, there isn't a way to unregister them from an internal process unless you hijack it yourself and then basically destroy the object and recreate it. You can't do it from external because it's an internal code object.
All right. Then the other question is also solved.
Brilliant,
right,
no problem.
Thanks.
Are there any other questions?
We have time for another question? No? Okay.
Brilliant.
Well done. Thank you very much.
Thanks for listening.